Okay, let's turn to Chapter 2. The title of the chapter is Time Domain Analysis. So we'll be looking at solving differential equations in this chapter in the time domain. And the first section is an introduction, where I'll use the introduction primarily to introduce some notation. So the systems we're working with can be described by a differential equation. In the general case, might involve various derivatives of the output y with respect to t. So I'll write in the general form a linear constant coefficient differential equation. This is the derivative with respect to y again, and then this would continue plus a n minus 1 dy dt, and then finally plus a n y. So in this general case, allowing the differential equation to have up to capital N derivatives with respect to y, and then for the input, the highest order derivative is capital M, so the derivative with respect to x, the derivative of x with respect to t, and then we can have various constants here, dm minus 1 of x with t with respect to t, dm minus 1, and then d minus 1 dx dt, and then finally plus bm x of t. This is a fairly general equation. The y terms all involve the coefficients y. Notice that on the highest order derivative term, the assumed constant, there's an assumed 1 multiplier here. We can always force that term to be 1 by dividing both sides of the equation by whatever that term is. So this is a general representation of a differential equation where the a's are associated with the output or y terms, and the b coefficients are associated with the input terms. So in our operator notation, we can represent this as d to the n represents an nth order derivative plus a1 d to the n minus 1 plus a to the n minus 1 d plus a capital N all times y, and then similarly for x, we'd have b0 d to the m plus b1 d to the m minus 1 plus this coefficient b of m minus 1 times d, finally plus b of m all times x. Or more generally, we could recognize this as a polynomial expression involving the a coefficients, and this is another polynomial of mth order in D. So I can simplify the notation slightly, and I'll call the polynomial in D on the output side of the equation. I'll call that Q of D, and on the right hand side, the notation we use for that polynomial is P of D. So you'll see this notation throughout the course. Again, this Q of D polynomial represents we can get this Q of D polynomial directly from the differential equation. You can write this down by inspection. So for example, if I had dy squared dt squared plus 3 dy dt plus 2y then is equal to 3 dx dt. The corresponding Q polynomial directly from the left-hand side, because my highest order derivative here is a second order derivative, would be d squared plus 3d, pulling the 3 down here, plus 2. So this would be my Q polynomial, and I can write that down again by inspection. The P polynomial is from the right-hand side, and this would be 3d and then plus 0x, and so I can just leave off the 0, but this would be the corresponding P polynomial. We will represent the output as the sum of two components. Okay, so and we're going to turn our attention to finding these two components. And I'll call the components y0 of t and yx of t, where y0 of t is defined to be the zero input response. So this is the output due to any initial state, like any voltages on capacitors, any current, any initial currents through inductors. But this is the component of the output that when the input is 0, it's due just to the initial conditions. And the other component of the output, called yx of t, is the component due to the input only, with all state conditions set to 0. Okay. Now, these two components, they're similar to the zero input response, is similar to what you may have called the homogeneous response in your differential equations course, and the zero state response is similar to the particular solution. They're not quite the same. They are related, and we'll see that later on as we continue through the course. In engineering, it's easier to actually, in most engineering problems, it's easier to separate the output into a zero input response and a zero state response. We'll be, in particular, later on in the course, we'll be concentrating on the zero state response, the portion of the total response that's due to the input, and this will actually lead to our transfer function.